Good morning friends, I am Chetan Dhajaya, Assistant Professor at SMC College of Dairy Science and one of the content writers for paper 12 and module 13, packaging of fresh fruits and vegetables. In this module, we will discuss about the different packaging methods and packaging materials used for fruits and vegetables. What is the requirement for the fruits and vegetables for the packaging and care to be taken for such material will be discussed in this module. Now friends, the demand for fresh fruits and vegetables is continuously increasing, but their preservation is still a challenge for food industry as their ability to respire or breathe. Apart from common physico-chemical and microbiological degradations, there can be degradations from respiration, transpiration and ripening. Such reactions are influenced by processing, storage and distribution conditions which deteriorates the initial quality of fruits and vegetables. Temperature and processing can help in preservation if properly controlled. Lower temperature reduces the rate of reaction and packaging may avoid dehydration as well as vapor saturation. Several changes take place in the quality of fruits and vegetables such as changes in sensory quality, microbiological quality and nutritional value. Now looking to the respiration and ripening, fruits and vegetables are live product and obtained all the nutrients from the growth from the parent plant. When they are detached from the parent plant, they draw on their own reserves to achieve aerobic respiration and maintain their cellular integrity. During respiration, stored carbohydrates are broken down into glucose, which is oxidized into carbon dioxide, water and energy. And these substrates become unavailable. Other carbonated resources such as constitutive protein or membrane lipids are used, leading to the death of the product. Thus, the potential shelf life of fruits and vegetables is closely related to their respiration rate. The respiration rate is specific to a particular fruit or vegetable in terms of species and varieties, but may differ depending on its maturity and mainly in climacteric fruits like peaches, apples, kiwis, etc. Minimal processing such as peeling, slicing and destoning cause mechanical stress and result in an increase in respiration activity from 2 to 8 fold and stimulate ethylene production from 5 to 20 fold. By increasing the bounded surface area, mechanical stresses also result in enzymic alteration in fresh commodities such as enzymic browning or pectin degradation and increased proliferation of microbial spoilage. Dehydration is another way of degradation. In association with aerobic respiration, water vapor is produced and natural dehydration occurs, caused by diffusion of water vapor from the high concentration components in fresh product to the low concentration in the surrounding environment. Marketing of items that have suffered significant water loss becomes very difficult. As fruits and vegetables contain more than 90% water, a loss of 5% or more water is visually noticeable, lowering the grade of the produce and resulting in a decrease in its commercial value. Now, major effects of water loss are a reduction in weight and a wilted appearance. There is also a reduction in nutritional value as the amount of water soluble components decreases when water is released. A loss in aroma and flavor and an enhanced sensitivity to chilling injuries. In case of climacteric fruits, water loss can accelerate the climacteric crisis as observed in the case of avocados. Although excessive dehydration is not recommended, whatever the product, moderate dehydration may be beneficial to some vegetables such as bulbs or common mushrooms. Looking to the effect of temperature, temperature is one of the major factors affecting shelf life of fresh products and needs to be controlled during handling. Respiration of raw fruits and vegetables increases 2 to 3 folds for every 10 degrees rise in temperature. In case of fresh cut produce, this factor may increase by 3 to 8 folds, and by increasing temperature, the rate of enzymic reactions and respiration is reduced. For climacteric fruits, post-harvest storage at low temperatures might be necessary to allow ripening. Refrigeration appears to be the most appropriate method for fresh produce preservation, but it is not always easy to achieve in retail distribution. In addition, it does not suit all commodities as observed by the development of chilling injuries such as core flush or soft scald in case of exotic fruits that are often combined with a rise in respiration rate. If we see the effect of composition of gas in the surrounding areas, which is another factor affecting respiration and consequently the overall quality of fresh produce, usually lowering the oxygen level, that is less than 2%, is really effective in reducing respiration rate. But anoxia, which means promoting the anaerobic catalysm and growth of anaerobic flora that produce undesirable of flavors, should be avoided. High carbon dioxide levels might also reduce the respiration of several commodities such as onions, strawberries or cucumbers, and can limit the production of ethylene as observed in kiwi fruit or inhibit its production as observed in tomatoes. High carbon dioxide levels induce a bacteriostatic effect on aerobic bacteria, but might lead to the development of anaerobic flora. Injuries might occur when a fresh product is exposed to a level of CO2 above its tolerance limit. Formation of brown spots on lettuce or yellowing of mushrooms are common visual degradations caused by high carbon dioxide content. Together with carbon dioxide, 1-methyl cyclopropane is also considered as a competitive inhibitor of ethylene action and can be used to delay ethylene production and the respiration crisis. As the optimal combination of oxygen and carbon dioxide greatly depends on the respiratory activity of the product and its sensitivity to carbon dioxide, there is no unique atmosphere composition that could be applied to all fresh commodities. Critical concentration of oxygen and carbon dioxide exists for each fruit or vegetable. Packaging materials must be properly chosen for each product, otherwise the headspace atmosphere may be inefficient or detrimental. Or modified atmospheric packaging. In 1930s, controlled atmosphere was used while shipment of fruits and vegetables, where low concentration of carbon dioxide and oxygen was used during the shipment, and from this the concept of MAP has been raised, in which low concentration of oxygen and moderate concentration of carbon dioxide is used inside the packaging material and surrounding the product. The biaxially oriented polypropylene or low density polyethylene and polyvinyl chloride are synthetic polymers used as trays, pouches or overwraps for packing of fresh fruits and vegetables. However, in most cases they need to be perforated to allow sufficient gas and vapor transfer. Two kinds of perforated materials are available. The first is macro perforated films that slightly protect the produce against dehydration by slowing down water vapor transfers, and the other is micro perforated films that provide a large range of oxygen permeabilities and can be tailored to the oxygen requirement of most produce. When synthetic films are perforated, the effect of temperature on permeation through pores or air is much compared to the effect on permeation through the polymer. As permeation through the pores account for most of the total permeation through the perforated film, the activation energies for perforated films are close to 0. Thus, perforated films are not able to compensate the effect of temperature variations during storage on the respiration rates of fruits and vegetables. Now, protein based materials. The development of hydrophilic materials such as protein based films appears to be of great interest to replace perforated materials in many applications. The film forming ability of proteins and polysaccharides from renewable sources is known and widely used for a long time, especially in the fruits and vegetable industry. Although most of the commercial plastic films are relatively unaffected by relative humidity, gas permeability of protein based films sharply increases at high relative humidity, such as in fresh fruits and vegetable packaging. For example, at 23 degrees Celsius, carbon dioxide permeability is 570 times lower for wheat gluten film stored at 0% relative humidity than for LDP stored under the same conditions, and it is 10 times higher for wheat gluten film stored at 95% RH than for LDP stored under the same conditions. The same effect was observed with oxygen permeability, but to a lesser extent. Consequently, the perm selectivity of wheat gluten films is also affected by relative humidity and ranges from 5 in a dry atmosphere to 30 under 95% RH. The increasing RH effect has been attributed to a modification of the wheat gluten network structure and polymeric chain mobility related to a change from a glassy to a rubbery state. The fact that carbon dioxide permeability is more affected than oxygen can be related to specific interaction between carbon dioxide and the water plasticized protein matrix under high RH conditions. Water sorption could provide better accessibility to active sites for carbon dioxide sorption onto the protein matrix, mainly hydrogen binding with glutamine residue. Thus, generated modified atmosphere can be both low in oxygen and carbon dioxide as described for modified atmospheric packaging of common mushrooms. Temperature also affects gas permeability of protein based films, and this is more pronounced in films stored at high RH as observed for oxygen and carbon dioxide permeability, as well as ethylene permeability of wheat gluten films. When stored at high RH, ethylene permeability of wheat gluten increases 5 times when temperature increases from 23 degrees Celsius to 45 degrees Celsius. Such behavior is of great interest in delaying ripening of climacteric produce during shipping and distribution in case of temperature abuse. Fiber based and protein composites. Combination of wheat gluten proteins with fiber based materials such as paper and so called composite materials have already been studied to overcome their poor mechanical properties. Recently, the combinations of wheat gluten proteins with nanofilters such as monomodulatonin have been demonstrated to be an efficient way to reduce the drawback of moisture sensitivity. Thus, combining wheat gluten proteins with pepper and montmodulonitin to produce so called non-composite materials, which could make the most of the functional properties of wheat gluten proteins while overcoming the drawbacks of insufficient mechanical properties and moisture sensitivity. Paper coated with wheat gluten solution can no longer be considered as a porous regarding oxygen and carbon dioxide permeability. The presence of MMT in the wheat gluten network did not significantly affect permeability. As permeability is known to be governed by two mechanisms, that is diffusion and sorption, it was assumed that introduction of MMT did not change solubility nor diffusivity of oxygen and carbon dioxide. It should be pointed out that oxygen and carbon dioxide permeability of both coated and nanocomposite material increasing with increasing RH. As this phenomenon was also observed with pure wheat gluten films, it suggests that wheat gluten based coating layer is the key element of gas barrier properties of the studied material, whether it is composite or non-composite. As a consequence, gas perm selectivity was highly affected by RH and rose from 1.9 to 7.9 and 1.5 to 7.5 for coated and non-composite materials respectively. These results show that unique gas perm selectivity properties of proteins are preserved when combined with paper or MMT. Another promising application of protein based material is their use as antimicrobial packaging. This relies on the ability of bio based polymers such as proteins to carry active compounds and release them in a controlled way according to a moisture and temperature triggering effect. The use of plant derived antimicrobial compounds as natural preservatives has received increasing interest in recent years. The efficiency of thyme, clove and oregano essential oils was related to the presence of phenolic aroma compounds thymol, eugenol, carvacrol respectively. Carvacrol was added to wheat gluten coating solution with or without MMT to produce nanocomposite or composite papers respectively. Release of the volatile compound was assessed at 25 degrees Celsius on all materials as a function of time and using a two-step gradient of RH. This RH gradient was used to stimulate the average storage condition of materials and the conditions when used for packaging of food such as fresh or minimally processed fruits and vegetables, generating an atmosphere close to 100% RH inside the package. Future trends: modified atmospheric packaging has the potential to prolong shelf life and quality of fresh fruits and vegetables, but the development of innovative materials is still required. To be effective, innovation should be conducted according to the integrated approach combining modeling and material science with the plant physiology and food quality. Modeling tools could enable the definition of targeted functional requirements for designing materials that should maintain produce quality by using properly chosen mathematical models and input data. So, friends, in this module we have seen the requirements for the packaging of fruits and vegetables and the packaging material, different packaging materials used or can be used, and the future trends for the packaging of fruits and materials, etc., and all these things that we have discussed in this module. Thank you.